So today, our mathematician spotlight is Katherine Johnson. This is not a picture of Katherine Johnson, but this is someone who played Katherine Johnson in a major motion picture. This is more like Katherine Johnson, so this is like what she looked like when she was the age portrayed in the movie Hidden Figures. She was a mathematician at NASA, and its predecessor. She calculated trajectories for many space flights, the first American in space, the first American to orbit the Earth. And she did things like created backup systems in case the computers failed, because that was when computers were new and people didn't really trust them. So for example, perhaps you know Apollo 13, the mission went wrong, and so she figured out this way that they could use just one star to pinpoint their location and then come home safely. It's pretty cool. And she also helped NASA transition from human computers, she was called a computer, to machine computers, what we would consider to be computers. So here is her later in life, and then here's her very recently receiving the Presidential Medal of Freedom from President Obama, which is the highest possible honor for a civilian. So I thought I'd let her talk to you instead of me telling you about her, although I've already done that. So here she is at age 97.
Well, now, if they just did the hard work that I did, which was my job, I did it every day. I never missed a day. Never stayed home playing stick and stuff. But my problem was to answer questions. And I did that to the best of my ability at all times. Correct or incorrect. But that's my theory. Do your best all the time.
So NASA built a new building and named it after her a couple of years ago.
I'll be exceedingly honored, greatly honored. But you know, math is the same. I gave you that answer last year. It's the same answer. But the main thing is I liked what I was doing. I liked work. I liked the stars and the stories we were telling. And it was a joy to contribute to the literature that was going to be coming out. But little did I think it would go this far.
All right. So, pretty amazing, wonderful life. One of the things that's a theme of all the mathematicians that I'm spotlighting with all of you, is that they're all alive. And so probably Katherine Johnson isn't doing math anymore, but she is alive. So this is really great. Okay. Not like that. Okay. Okay, great. So if you become a mathematician or you major in math, which I encourage you to do, you don't have to become a professor or go into academia. There are many places you can do math. You can do it at NASA, you can do it at the National Security Agency, or you can take your mathematical training to anything. Politics would be great, theater, anything you want. Music, anyway, anything. This will help you no matter what. Okay, so the theme for the last couple of weeks of the semester is that we will integrate scalar and vector valued functions over surfaces. So we're going to integrate those. And we talked about scalar surface integrals the last time, and we did an example. So this we've done. We did it last time. And we'll also do it today. And then today we'll start talking about vector surface integrals. So integrating vector functions over surfaces. So we'll start today and then do it for the rest of our time together. So there are two big theorems, the divergence theorem and Stokes' theorem, that we'll talk about, which relate to vector surface integrals. So that's the goal. Okay. But we'll start with a scalar surface integral. As is our custom, we'll start with the old thing and then start the new thing. And then continue on with the new thing. Okay, so suppose you have an aluminum can which used to contain beans. But you ate the beans and you didn't wash the can and recycle it. So now it's growing mold and you kind of forgot about it. And so it's very moldy. So let's say the amount of mold on the can at the point x, y, z is given by f of x, y, z is x squared plus y squared plus z. So this says the further you go out in the can, the more moldy it is. Kind of makes sense. There's more beans on the outside. And then the further you go up, the moldier it is. For whatever reason, maybe because the spoon was closer and your mouth was closer, so it got yucky. Okay, so we want to know the total amount of mold on the thing. So compute the total mold on the can. Okay, and here's what the can looks like. I'm not sure actually what its radius is. Its radius is just some a. And I'm not sure what its height is either, because you guys are probably using different cans. So we'll just say that its height is h. And we'll put it, since this depends on x, y, and z, the z-axis goes through the center of it, and the bottom is on the xy plane, z equals 0, and the top is at z equals h. So this sets our can in space. And we want to compute the total mold on the can. Okay, so we'd like to set up a surface integral over the whole surface, but it's kind of like 3 separate surfaces. So the can has this top part, T, it has this bottom part, B, and then it has this cylinder part, let's call it C. There's not really any way to compute the surface integral of all of them all at once because they're so different, so let's compute them separately. So if let's say the whole surface is S, then the double integral over S, we want to know the double integral of f ds. So that means at any little point here of the surface, we want to know what's the value of the function, how much mold is there, times the little surface area of that little piece. And then add that up over all the little pieces of the surface. And so that'll be the double integral over the bottom plus the double integral over the top, plus the double integral over the cylinder of that same thing, f ds. So let's compute these separately. So first, the amount of mold on the bottom. Okay, so I could set up a scalar surface integral. One thing we did at the end of class last time was we set up a scalar surface integral over the xy plane. And what we learned from that was that it's just the same as doing an area integral like we used to do before we started doing surface area integrals. So probably the best thing to do is just, this is a disk in the xy plane. Let's just do a double integral. So we want to do the double integral over the bottom of f ds. So that's the double integral over the closed disk of radius a of f. So f is, here it is. I'll highlight it here so you can see it better. F is x squared plus y squared plus z, and then ds. But our surface is just the xy plane, so we call that dA. So just dA. There's an error. I made an error on your sheet. I called it the unit disk, but actually it's a disk of radius a, so you can fix that. Okay. Also, so let's set this up. Z is 0 on the bottom because it's in the xy plane. So this is just 0. And x squared, let's see. We could do this in x and y coordinates, but it would be better to do it in polar coordinates because it's a circle. So let's set this up in polar coordinates. We want to go from theta equals 0 to 2 pi, and from r equals 0 to a. By the way, this is an a because it's a disk of radius a, so I made a mistake on your sheet. It has a 1, but it's an a. Of x squared plus y squared plus 0. So that's just x squared plus y squared, which is r squared. So r squared, and then dA, which is r dr d theta. So this is just setting up an integral of x squared plus y squared over the disk of radius a, something you've done before, probably, well, at least something close to it. So this is the integral from theta equals 0 to 2 pi. Let's see all the thetas, only d theta, times the integral from r equals 0 to a of r cubed dr. So the first integral comes out to 2 pi, and the second one comes out to r to the 4th over 4, so a to the 4th over 4. Okay? Yeah. Okay? So let's do the top, which will be similar. So the second part we'll do is the amount of mold on the top. So you'll notice that this amount of mold on the bottom depends on A. So the bigger the can is, the bigger the radius is, the more mold there is. It kind of makes sense. Okay, the amount of mold on the top is the double integral over the top of f ds. So again, we can imagine that our region of integration is just a closed disk of radius a in the xy plane, because it's just the closed disk of radius a lifted up by a height of h. So this is the double integral over the closed disk of radius a of f. And now f is x squared plus y squared plus z. And again, des is just dA. But now z is something different. Z isn't 0 this time. It's h. Yeah, it's a constant value of h. So this is just h. Okay, let's set this up in polar coordinates. So again, theta goes from 0 to 2 pi, and r goes from 0 to a. This is a, not 1. And x squared plus y squared is again r squared. And z now is not 0, it's h. And then dA is r dr d theta. Okay, and now we just compute this. So h is a constant and r is a variable. Let's pull out our theta. So theta goes from 0 to 2 pi. We're integrating d theta times the integral from r equals 0 to a. I'll distribute the r cubed plus hr dr. So this first integral comes out to 2 pi. And then the second one, so that's multiplication. Integral of r cubed with respect to r is r to the 4th over 4. And we plug in a, we get a to the 4th over 4 plus, so the integral of r with respect to r is r squared over 2. We plug in a, we get h a squared over 2. Okay, so that's some number. This is the amount of mold on the top. You'll notice that this term, the 2 pi with the first part, is the same as what we got for the bottom, because that just depended on the radius. But then we have a bit of extra. It gets moldier as we go up, x squared plus y squared plus z. So it's a bit moldier on the top by this amount. Yeah. Questions or ideas? Okay, so that was a clever thing. We noticed that our top and bottom were horizontal, so we could just do it as a double integral as before. But our cylinder part, this is different. This is curved. It's up in space, so we'll have to do this separately. So for the third one, for the amount of mold on the cylinder part, we'll have to parameterize the surface. Okay. So let's see. I'm going to draw another picture of the surface over here so I don't have to keep walking back and forth. So here's our surface. Here we are at h. Here's 0. It has radius of a. And we want to parameterize this x of something comma something. So we need 2 parameters just to parameterize the curved part. So this part here. So if that means I want to pick some, if I pick some point on it, how can I specify it? So there are many ways you would do this. But one way would be, you could think, well, first, I want to know where it is on the circle, like how far around it is. So you want to specify like the theta where you are. So maybe our first variable could be theta. And then once you know where you are on around the cylinder, you have to know how far up you are. So we could use z. So 2 good parameters for this are theta and z. It's basically like if you cut this open and turned it into a rectangle, it would basically be like x and y. But here it's theta and z. Okay, so we can parameterize this with theta and z. So we have an x coordinate, a y coordinate, and a z coordinate. The z coordinate is z. And then to get x coordinate and y coordinate out of theta, well, it's just a circle of radius a. So we would do like cos theta sine theta if it were a circle of radius 1. But we do a cos theta and a sine theta to get a circle of radius a. Okay, so this parameterizes our surface. Okay, so here's the plan. We're going to need some things. We're going to need the derivative of x with this. We're going to need the tangent vector in the theta direction. We're going to need the tangent vector in the z direction. We're going to need the cross product of those two vectors. And then finally, we're going to need the magnitude of the cross product of those two vectors. Because what we want to do is we want to compute the double integral over the surface of f ds. And I'll just remind you how we do that. That's the double integral over the region that we're interested in the theta z plane of f of, well, x, y, and z, whatever they are. So f of our parameterization, x of theta and z, times the magnitude of this, well, this normal vector, x theta cross xz, times dz d theta. OK, we derived this the last time. The idea is you want the value of the function at each point, and then times the area of the little parallelogram where you're computing that thing. And then we're going to add that up everywhere. So we'll need all these parts. And this is analogous to the Jacobian expansion factor. It's just like a Jacobian expansion factor, but up in 3D for surfaces. So let's compute all these things. OK, so x theta. That means, suppose that I'm here at my favorite point, and I hold my other variable, which is z, constant, and I just change theta a little bit. I increase theta a little bit. Which way do I go? So it would be the vector in this direction. So let's compute it. We get the derivative with respect to theta of a cosine theta is negative a sine theta. With respect to theta of a sine theta is a cos theta. And then the derivative of z with respect to theta is 0. So let's see if it makes sense. OK, so if we're not changing z at all, we're only changing theta, it makes sense that our z coordinate wouldn't change at all. We have a 0 here in the z coordinate. We're just staying on the level. And then this, so a sine theta is our y, and a cos theta is our x. So this just says it's negative y comma x. Negative y comma x. We know that guy. What negative y comma x is the counterclockwise. I was trying to figure out which way is counterclockwise. The counterclockwise vector field. And that makes sense. It is going counterclockwise. So it looks right. OK, and now let's do the same thing with z. So the partial derivative with respect to z means if you keep theta constant, so you're not going around the circle at all, but then you increase z a little bit, which way will you go? So I think it's pretty clear that you just go up if you increase z. So we're hoping to get 0, 0, 1. Let's see. Derivative of this thing with respect to z. There are no z's in it, so it's 0. Same here. Also 0. Derivative with respect to z of z is 1. Yes. OK. And now we want to take their cross product. That'll give us a normal vector. So if we take x theta cross xz, it means you take your fingers, you put them in the direction of x theta. You have a right hand. OK, yeah, you have to use your right hand. OK, you put them in the direction of x theta. Not sure if I should put my hand this way or this way. OK, then you curl them in the direction of xz. And then your thumb points in the normal direction. So we expect this to be pointing out towards us. So in particular, let's see, we expect a z coordinate of 0. And we expect that it'll be very much like the vector out to the point xy. Let's try it. I'll color code this so that we know what we're doing. OK, so x theta cross xz, they're all written here. So you can imagine I had I, j, k written here. So we do a cos theta times 1 minus 0 times 0 is a cos theta. Then negative of negative a sine theta times 1 minus 0 is a sine theta. And then 0 minus 0 is 0. Huh. So we got a z value of 0, which we expected. We just come horizontally out. And then this is our x, and this is our y. So it's like we went in the direction out from the z-axis to our point xy, and then we kept going more, and that's our normal vector. Kind of makes sense. So it looks right. OK, and now we want to find the magnitude of this thing for our Jacobian expansion factor. So if you do this thing squared plus this thing squared, you get cosine squared plus sine squared is 1, plus 0 is 0. OK, so this is the magnitude of the square root of a squared which is a magnitude of a, oops, not a vector, which is just a, our radius. Okay, I think we're ready. Well, let's compute this thing. So, yes, I was remiss when I parameterized the surface not to say which values of theta and z we want. So let's fill those in now. So the values of theta we want and the values of z we want. So theta, we want it to go all the way around, so 0 to 2 pi. And z, we want it to go from the bottom at z equals 0 to the top at z equals h. So z should go from 0 to h. Okay, so now we're ready. So let's see, we want the double integral over the region in the theta z plane that we're interested in. That's exactly this theta and z. So we want theta to go from 0 to 2 pi and z to go from 0 to h. Okay, then we need f at each point of our surface. So f of x, y, z, I'll write this somewhere, maybe up here to remind us. F of x, y, z is x squared plus y squared plus z. It's been a long time since we used that function, like a few minutes at least, but that was the function that gives the amount of mold at each point. So we have to do f of whatever our x is. This is our x. So it says take x and square it. So a cos theta quantity squared. Then it says take whatever y is and square it. So a sine theta squared. Then it says take whatever z is and add it. So that's z. Okay, so this part here is our f. Okay, and since f is the amount of mold, we'll color code it in green. So f of x, y, z is that. Okay, then times the area of the little parallelogram, well, the big parallelogram, okay, times the Jacobian expansion factor, which is a times dz d theta. So this part here was the magnitude of x theta cross x z. Okay. And now we just compute it. Now we have all the parts, and we just have a double integral to compute. So let's write it down. So this is the integral from theta equals 0 to 2 pi of the integral from z equals 0 to h. Cos squared plus sine squared, still 1. So this is a squared plus z, this integral, times a dz d theta. So we don't have any thetas in here, so we can pull it out. This is the integral from theta equals 0 to 2 pi d theta times the integral from z equals 0 to h of what? A cubed plus az dz. Okay, so this first integral is just 2 pi. And then this last one, let's see, the integral of a constant with respect to z is just z times a constant. So this is a cubed times h minus a cubed times 0 plus the integral of z with respect to z is z squared over 2. Put in h. I think we get a h squared over 2. Okay. Okay, so this is the amount of mold that's on the cylinder. So what we did there was we parameterized the surface. Then we did a bunch of things to get our Jacobian area expansion factor thing with our magnitude of our cross product. And then we just plugged into our integral equation and turned it into a double integral and computed it. Yeah. So we can triumphantly conclude then total mold on the can. The double integral over this on the whole surface of SDS is the amount on the bottom plus the amount on the top plus the amount on the cylinder. Here I'm omitting FDS because it's the same everywhere. So it's the amount from the bottom, which was 2 pi times a to the 4th over 4, plus the amount that was on the top, which was 2 pi times quantity a to the 4th over 4 plus ha squared over 2, plus the amount that was on the cylinder, which we just got, 2 pi times a cubed h plus a h squared over 2. So if you wanted to really know, then you would just add them all up. Yeah. Yeah, questions or ideas? All right, we're wearing the same outfit. We did not plan this. We are both wearing dark blue with white anchors. Interesting. All right. It's a good choice. All right. Okay. So that's the idea of surface integrals. So in this class, we've learned to integrate lots of things. We've integrated lots of different kinds of functions over geometric objects. So for instance, we integrated functions over regions of the plane. We integrated functions over solids. We integrated functions over curves and also vectors, vector fields over curves. And we've now integrated scalars over surfaces, and we're about to integrate vector fields over surfaces. So in all those, the idea is you have some geometric object, like either a curve or a piece of surface or a chunk of material, and you have a function that gives a value to it at each point. And you just want to add it up over your whole object. So integration, that's the whole idea of integration. You add up some function values over some object. So what we're going to do is vector surface integrals. So I'll write that down. So here we start with vector surface integrals. So I encourage you to think about vector line integrals as like wind and you're walking along a path. So think of them that way, and then you can also think of like conservative vector fields as how hard it is to hike when you're walking on a path, and the function is like the gradient is the vector field is a gradient function of your elevation. So that's a good way to think about line integrals. For surface integrals, I suggest that you think about it as like a stream with little tiny fishes in it, like krill or something, so small that you can't really see them. They kind of just flow with the water. So, and then you have a net and you're trying to catch them. And you wonder how many of the fish are like getting caught by your net. There are some places where the metaphor breaks down. Like if it's flowing backwards through your net, you lose fish, get negative fish. But I think the metaphor is pretty good. So, vector surface integrals. Okay, so you're given a flowing stream full of tiny fish. And what I mean by that is you're given a vector field F. So our vector fields are usually red. So we have some sort of vector field F here. It's doing its thing like vector fields do. And you can imagine that this is a flowing like waterfall or something, whatever. Okay, so there's your F. And there's fish that are just, oops, those are backwards fish. Fish which look very much like the letter alpha, but that's how you draw a quick fish. Anyway, they're flowing just with the stream. And then, so given a stream full of tiny fish and a net with an inside and an outside. Oh. So this is a surface, but it's a surface with a chosen direction. So here's our vector field F. Yep, I labeled it. And then here is our surface. So maybe our net looks something like, so there's our surface. And then you have to pick an orientation. Either it's oriented out or it's oriented in. And you can think of that as like the direction you are wishing that the fish will go. So if I want this to be the inside, I would orient my net going out like this. And these are unit normal vectors that are perpendicular to the surface. They're all supposed to be unit length and perpendicular to the surface. Okay. So you're given a stream full of tiny fish, which is a vector field, and a net that you have an inside and outside. The vector surface integral of F over S measures how much F flows through your surface in the direction that you like. So F flows through S in the preferred direction. And the way that you do this is you take the double integral over the surface of F dot n ds. Okay, so what this means is at every point of your surface S, you ask, are F and n pointing in the same direction? So the dot product, as you might remember, measures how much two vectors are pointing in the same direction. So this measures how much f and n point in the same direction. And you want to add this up over this whole surface. Okay, so the idea is at every point you say, hey, are they going the same direction or not? So for example, at this point here, it looks like our normal vector is going here, and maybe our vector field is going here. So our normal vector looks like that, and our vector field vector looks like that, and here f dot n is positive, because they're pointing in the same direction. On the other hand, I will somehow, I'm going to erase this one there and make it look more like that. Because now up here, f and n are perpendicular. So with this picture at the top, here's n and here's f. And they're perpendicular, so f dot n is 0. You can take f dot n being positive to mean that you're catching fish. They're flowing right into your net. And you can take f dot n being 0 to mean that the fish are just flowing right along your net. What a nice place to swim, they're saying, and they're just flowing right along. You're not catching or releasing fish, you're just holding on to them. And then if they're going in the opposite direction, I haven't drawn that here, but maybe the net goes around like this, and so we have a point here. So it's some kind of weird net like that, maybe. So we have a point here where the vector field is pointing this way, and the normal vector, the outward normal vector, is pointing this way. And so then in that case, f and n point in opposite directions, so f dot n is negative. And so you want to add this up in all the places to see what's happening. Are you basically catching fish or basically losing fish or whatever? So that adds this up over the whole vector field. Yeah. OK. So if you would, on your sheet you have a picture of some surfaces with the chosen orientation and some vector fields. And I'd like you to decide if the surface integral is positive, negative, or 0, and then talk with your neighbor about it. Are you writing? OK, so Nuseba is going to talk about what is going on. Can you say why?
Why?
Yeah. The dot product will be positive? Can you say why?
I was thinking off of the big example where
Yeah, it's okay. It's okay. Because the vector. Can somebody say why? The dot product is positive? Choose a friend.
Because they're in the same direction. They're pointing in the same direction, so.
Yeah. Yeah, nice. The pink are basically going up, which is the direction that you wanted. And that's the direction n is going. Nice. Okay. Yay.
this one has because the series is dot product perpendiculars.
The vectors are perpendicular? So their dot product is.
The vectors are perpendicular.
Nice.
And then for this one we have this one I'm not really sure because and I have the book created.
What do you guys think? Call a friend. So can you explain what changed your mind, or why it should be 0?
Like some of them are going positive and some of them are negative, so it's a equal amount of things.
Nice. Yeah. Great.
The last one I also had
Nice. Great. All right. Thank you. Yay. All right. Great. Yeah. Yeah. So the idea is that this vector line, the surface integral thing, measures how much the vectors point in the same direction. Sometimes they're all pointing with the vector field, sometimes they're all pointing perpendicular to the vector field, but often there's some that are pointing with and some that are pointing against. Like here, the vectors are pointing with the normal vector, and here they're against, and here in this case they happen to cancel out. And then right along this sort of vertical equator, or the prime meridian or whatever, I think they're all perpendicular. So, cool. Okay, so let's do an example of actually computing them, and then we'll come up with an equation, and then we'll be done. Yep.
I'm a little confused about the difference between what we're doing right now is from like line integrals.
Yeah.
Like we're conceptually like thinking about the same thing.
Yep, conceptually, it's very similar to line integrals. Except, well, one big difference is that we're integrating over a surface, right, instead of a curve. And the other difference is that with a line integral, you're using the tangent vector, so the vector that's going in the direction of the curve. And here with a surface, there isn't really a well-defined tangent vector, because to if this is your surface and you have, I'll curve it this way, a tangent vector at this point, well, there are many choices. So there's really just a well-defined normal vector. And so it actually makes sense to compute how much the vector field is flowing with the normal vector in this case. Yeah. And I should mention that this quantity is called the flux. This is a name invented, I think, by Newton. When he was invented calculus, he talked about it in terms of fluxes and flows for everything. Fluxes and flows. All of calculus, fluxes and flows. Okay, so here's an example. So let S be the unit square in the xy plane. And let F, I have to give an orientation. So oriented up. So now I'll draw a picture. So here's the x-axis and the y-axis and the z-axis. And here's the unit square. What I mean by unit square is just, here's a point 1, 0, 1, 1, 0, 1, and 0, 0. And so there's my surface S. And I have to decide, is it oriented with the normal up or the normal down? And I just decided the normal should be up. So there it is. And let F be some vector field that's horribly complicated in the x-coordinate, like cosine of xz. It's horribly complicated in the y-coordinate, like e to the y. And then the z-coordinate is 5. And the question is to compute the double integral over our surface of f dot n ds. Okay, so the first thing we should do is see what we expect. So the vector field, let's see. I don't know what it's doing in the x-coordinate, and I don't know what it's doing in the y-coordinate. I could probably figure it out, but I won't. But I know that the z-coordinate is always 5. So it's doing something crazy maybe in the x and the y, but it's always pointing up. Okay, what do you expect? Do you expect it will be positive, negative, or 0? Positive, yeah, because the normal vector is pointing up, and all the vectors are also pointing up. So we expect this to be bigger than 0. Okay, so now let's do it. So one trick is to notice that the normal vector, well, we chose the upward normal, and we always choose a unit vector for the normal. So it's just 0, 0, 1. So f dot n is whatever the first coordinate is, comma whatever the second coordinate is, comma 5 dot 0, 0, 1, which is 5. Yeah, something times 0 plus something times 0 plus 5 times 1, which is 5. So I could have made this more complicated. There, it's very, 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 very complicated. Okay, but it's 5. Okay, so now let's do the double integral over the surface of f dot n ds. Well, we know what f dn is. It's always 5. So that's the double integral over the surface of 5 ds. We can pull out the 5 because it's a constant. 5 times the double integral over the surface of ds. And actually, what I'm going to do is I'm going to call this 1 ds. And we know that if you integrate 1 over any geometric object, you get its length or area or volume or whatever. So this is 5 times the area of our surface, which is just a unit square. So it's 5 times 1, which is 5. Okay. So the idea here was that who cares what the x and the y are doing? The z is always pointing with our normal vector, and it's always pointing to the tune of 5. So we just get 5 amount everywhere. 5 concentration of fish everywhere. Okay, so this clever trick is analogous to our line integrals when they went horizontally or vertically, and we were able to simplify our lives in some way. But you might guess that this does not always happen. So let's come up with an equation for a vector surface integral all the time. Okay. So, to compute a general vector surface integral, okay, we're going to want to compute the double integral over S of f dot n ds. That's what we're going to want. So first we're going to need a parameterization of our surface. So like x of s and t, this is a parameterization of the surface. Okay, then we'll need our vector field at each point. So f of x of s comma t. This is like the vector field at each point. Okay, n. So n is a unit normal. So let's find a normal vector and then turn it into a unit normal. So a normal vector to s is given by, let's see, did we do it? I erased it. It was right here. So it's xs cross xt. So the idea is you take a vector in the s direction on the surface, that's tangent to the surface. You take a vector in the t direction on the surface, that's tangent to the surface. So when you take their cross product, you'll get something that's perpendicular to both, so something that's normal to the surface. And then what we need is we want this to make a unit normal. So unit normal would be this same thing, xs cross xt, but divided by its size. So divided by xs cross xt. Okay, and then finally we need ds. So ds, that's like a tiny infinitesimal piece of surface. So we imagine we have our surface here, and these are s curves and t curves, and we have a curve in the s direction, so here's xs, and then we have a curve in the t direction, so here's the tangent vector to that, xt, and we just want to go a tiny little bit in that direction. So what we do is we go a bit in this direction, a little bit in that direction, so we use the vector xs times a tiny little distance ds, and we use this one, xt times a tiny little distance dt, and that gives us the vectors for this little tiny parallelogram, and then the area of it is ds. So ds is the magnitude of xs ds cross xt dt. Because the magnitude of the cross product is the area of the parallelogram spanned by the two vectors. So and ds and dt are just constants, so we can pull them out. This is xs cross xt ds dt. Okay, so I think we have all the ingredients that we're going to need to write down this vector surface integral. Okay, so to compute a vector surface integral, so we want the double integral over S of f dot n ds. Okay, so that's the double integral over the region in the ST plane that maps to our surface, the part that we're interested in, of f of x of s and t. So that gives us, that's our f. It gives us the value, the direction of the field at any point. And we want to dot that with our unit normal vector. So xs cross xt over magnitude of xs cross xt. So this part here, this is our f, this is our n, our unit normal. And then we multiply by ds. So ds is magnitude of xs cross xt times ds dt. So you can see, just like happened in our scalar or our vector line integral equations, these two things cancel out. So we get that this is just a double integral over the region that we care about of f of x of s and t dot xs cross xt ds dt. And as before, I think it's not so easy to see why this is the right thing to do. The thing to do is to look at this equation and say, oh yeah, I got my vector field, I'm multiplying by a unit normal, and then I'm adjusting by my Jacobian area expansion factor, and these two things just happen to cancel out. So this is the formula we'll use in general for a surface integral, and we'll use it next time. All right, thank you.